My name's Chris Valasek, and this is Dr. Reverend John McDonald, Esquire. And we're here today to talk about practical Windows heap exploitation on XP, SP3, and 2000.
Want to stand up?
Sure.
Remember eye contact?
Yeah.
Okay.
All right, so this started off with, originally with arbitrary D-word overwrites, and retrospectively, this seems kind of simple. There wasn't any PEB randomization or any mitigations against, say, unlinking. And you could just overwrite, say, the PEB locking routine, call it, and then you had the win. Then in Windows XP Service Pack 2, they sent an email to John and I and said they wanted to make our lives living hell. So they changed everything and put in safe unlinking heap cookies, slightly more randomized PEBs, and I guess things are becoming more multi-threaded, and Vista is a total fail for us. So we'll go through a little bit of history here. There's been a lot of heap research done that was very good. We'll put an end to that today. And you can look at these few other talks here. They're all really good and all gave us a really good base foundation for our research.
Yeah, in particular, this is working. Brett Moore's talk is awesome, and if you look closely, like each pointer he has in his examples, like it looks like they're just example pointers, but if you go and look, each one could have been a little research paper on its own. He's that cool that he can just leave a pointer there as an explanation of an attack. But,
I think we both read over heaps about heaps like 20 times.
At least.
Yeah. Nico Weissman also rules, and Ben Hawks is doing great stuff with Vista. Things we're going to cover today, we'll go over the memory management foundations. These are core data structures, algorithms, security mechanisms, and then we'll go and look at some tactics. We'll go over the best of breed techniques that are out these days, and we'll try to throw our 2 cents into the ring, if we can. Thirdly, we'll talk about strategy, and we've kind of tried to develop a process that makes exploiting these vulnerabilities easier, a series of steps you can take and ask yourself as you go on. And then we have a video demo that proves absolutely nothing. So we're going to go over the fundamentals now. We're going to talk about the heap base, and John and I refer to this as the big baby Jesus of heap data structures. This contains a bunch of information about every heap that's created in Windows. There's a plethora of data structures in it, and we'll look at a dump from a debugging window. I don't know how well everyone can see that, but you have things such as the flags. These can change whether you start the application from a debugger or attach a debugger. The virtual memory threshold is the amount of memory that the Windows Heap Manager is willing to manage. If it's greater than this amount, the operating system deals directly with that huge memory. We'll go over the UCRs later, and the segments, and at 158 hex off, where you see the little bit of the lowercase u is the free list in use bitmap. Which we'll also go over later, and the large block index, which we'll refer to as the heap cache from here on out, and all the other bolded items. Oh, I guess we should talk about the commit routine.
Yeah, so that's kind of our, at 57C is a nice function pointer that's used to extend the heap. So when the heap needs more memory, this function is used to extend the UCR list, I think.
Yeah, I think so.
But this function, basically, you have a nice function pointer. If you overwrite the one on the process heap, it's at a relatively predictable, stable address. And in 2003, it's not encoded like most of the other function pointers.
Yeah.
So we ended up using O by 57 heap base plus O by 57C as a vector for a lot of our attacks.
Yeah. You control the function pointer, so I mean, I won't say it's easy for the win, but it definitely helps in the
right, and you
journey.
can point it at a function episode or whatever you need
exactly.
to beat that.
So heap segments are contiguous ranges of virtual memory, and these heap segments, they actually contain all the heap chunks for that segment. And there's certain debuggers, like Immunity Debugger, will actually walk the heap segments, telling you information about each heap chunk, its size, whether it's free, what its flags are, etc. So these are the way that the heap keeps track of its memory in use. And we'll also look at the debug dump of one of these. As you see bolded, there's the heap, which it's associated with. the first entry, the last valid entry, and the last entry in the segment. And again, these can be useful when doing your research or trying to get more reliability out of an exploit. Here's a little bit of memory layout, and John created this, and it's really good because the blocks that are protruding out are representative of memory that's already been committed. Not all memory, as we'll talk about later, gets committed that is backed by virtual memory right when it starts. So the long, slender pieces that aren't protruded are reserved memory, but nothing's been committed to them yet. Now we'll get to the front-end manager. The heap manager is broken into relatively two parts. You have the front-end manager, which is optimized for speed, and then you have the more robust back-end manager, which does basically everything else. We're not going to talk about the low fragmentation heap because of time constraints and lack of knowledge. So we'll just talk about the look-aside list today.
Honesty will get you nowhere in this business.
It's an array of 128 linked lists containing 48-byte data structures. These are free chunks of sizes less than 1024, and the index of each array multiplied by 8 gives you the size. So say look-aside list 4, that's 32 free bytes. Of course, eight of them are always reserved for the heap chunk header. And also noted that heap chunks in the look-aside list still have the flag set as busy. This is so that the free list won't go up from under it and allocate those chunks without its knowledge. There's a little bit of pseudocode. You see you pass it a size, it gets rounded up and divided by 8, and we'll call this the block size. It then checks if the size is less than 80. That's 80 times 8 is 1024. If it is, it tries to use the look-aside list. If it returns you a good entry, it'll return it. Otherwise, it'll continue on and try to use the free list. Now this brings us to the backend manager and the free list. These are 128 doubly linked lists this time of free chunks up to 1024 bytes. And each list has a sentinel node at the base of the heap, and it starts at 178, that's free list 0. We'll have to note that there's special free lists like free list 0 that contain all the chunks that are greater than or equal to 1024 bytes in size. Also, free list 1 isn't used, and just like the look-aside list, the index is multiplied by 8 for the size of the free chunks. 1 times 8 is 8. That's only enough room for the chunk header, hence there's no user data and it's not used. So we'll continue on. Here's a little diagram that got marked up today. You see that free list 1 and 2 are both empty because they point back to itself. And free list 0 has 3 entries, and these entries connect to each other and eventually point back to the sentinel node to denote the end of that linked list. This brings us to the free list in use bitmap. This is another optimization made in the heap. When a dedicated free list is attempted to be used, say we'll call this free list n, and it can't service the request, it'll actually scan the bitmap to find the next largest chunk that's available to use. And if the bit is set in the bitmap, it has free chunks in that free list. Otherwise, it's 0 and there's no free chunks. We'll talk about abusing this later to make the heap manager believe that there's free entries where there actually is not any. On to the algorithms. Do you want to talk about commitment? I'll do it.
Okay.
All right. I guess the diagram before kind of showed us this, the commitment and decommitment and kind of a graphical representation of this. The heap manager will reserve memory. That means it has a big address space that will reserve, but it doesn't actually back this with virtual memory yet. You have to commit memory for it to be actually backed with virtual memory. This is referred to committing, and decommitting is the inverse of that, taking committed memory and returning it to the reserve section. A lot of people you'll see if you try to read, write, or execute in non-committed memory, you're going to get an access violation. And I've referred to it as myself before writing off a page. If you're, say, doing an overflow and you write into memory that hasn't been committed yet, I guess that's kind of true because it commits it 1 page at a time, and you can say whatever you want. This brings us to the free list search. This is where the ball needs to find the hole, it needs to find its home. So it starts looking through the free list to determine where's the correct spot to put this free chunk. If there's a dedicated free list of that size, it can put it on there, and otherwise it can use free list 0. We'll go through the pseudocode for kind of how a search would actually pan out. The first thing, like we showed you on a previous slide, is it'll try to search the look-aside list first, and if that can service the request, we'll then return it. Next, if the look-aside list can't fulfill a request, it will still check that the size is less than 80, that is below 1024, and try to use a dedicated free list. As you see here, it'll access the dedicated free list. If it's present, return its backlink. Otherwise, you use the free listed use bitmap, you scan it and return its backlink. You also will check if it's above 1024, the first thing it'll do is check to see if the heap cache is enabled. And that's the large block index in the heap. If it is, it'll use this optimization to find a correct pointer to a sufficiently sized chunk and return you that. Lastly, if the heap cache is not enabled, it will go straight to freelist 0 for sizes above or equal to 1024. And the first thing it does is check its backlink. The backlink is the largest chunk in freelist 0. From that, it will, if it's large enough and the freelist 0 actually exists, well then it'll start at the beginning and start traversing forwardly through the free list. And this is an expensive operation if you have a huge free list 0, and this is why they implemented the heap cache to have pointers into free list 0 to kind of do a shortcut when finding sufficiently sized chunks. Just as there is linking, there's also unlinking. This is taking a chunk from a free list and removing it. These are where the safety mitigations were put into play to make our lives miserable. And what it'll do is, I kind of think of it in a three-step process, is if the heap cache is active, remove that entry from the heap cache. The safe unlink is obviously performed. And then if it's a dedicated free list, and it's the last entry on that dedicated free list, you're going to update the bitmap from it has free chunks to it doesn't have free chunks. And we're going to look at some pseudocode for this as well. As you see, the first thing it does is try to remove it from the heap cache. Then you have your typical safe unlinking and report corruption. You also note in XP Service Pack 3 and Windows 2000, the report heap corruption won't actually terminate the process. It'll continue executing. And Brett Moore covered this pretty well in his Exploiting Freelist 0 on XP Service Pack 2, because since execution continues, you can use that to your advantage. Then it checks the size, and if it's the last block, like I mentioned before, it gets the size and updates the bitmap accordingly. And this brings us to linking then. So linking will happen when a chunk is freed or a chunk is allocated and it needs to be split, returning the result to the application and the remainder back to the free list. It determines what free list it should be on, and then toggles the bitmap, like we talked about before, just when removing it. It finds an appropriately sized block, gets its backlink, that is a block that's bigger than itself, and then it links it in. And it should be noted that linking in doesn't actually have any safety checks. And this is what we'll talk about, and in our demo we'll show you how we abuse the linking to actually get the win. Here's again a little bit of pseudocode. If the size is less than 80, use the dedicated free list. Otherwise, is the heap cache enabled? If so, use that to get your reference block. Otherwise, iterate through free list 0, and then you see it link the structure in, or link the chunk in, I'm sorry. Everyone should pay close attention to the last piece of code in there. It's the afterbox backlink equals new block. This is where we take advantage of the linking in. Basically, if you can provide a malicious backlink, you can get that address, the address of the chunk you've just freed, to that address. And this is, again, these vulnerabilities and writing exploits for them are now multi-stage. You have to do 4 different techniques just to get to your end goal. Coalescing is the devil. It ruins everything all the time. Basically what it is it prevents the heap from becoming fragmented. And when you free a chunk, it will actually look at its neighbors, its previous neighbor and its next neighbor. And if either one of those are frees, it'll combine them together and make bigger chunks. It does this because you don't want to have a bunch of small chunks in your heap, and then when a large allocation request comes in, you're going to have to extend the heap, and that's an expensive operation. And I know in the coalescing algorithm, I used it for exploiting the D word overwrite before they introduced safe unlinking. I don't know if that was just me. I thought it was what everyone did, but who knows. Okay, now we're going to talk a little bit about security mechanisms. The first one we'll talk about is the heap cookie. This was introduced in Windows XP Service Pack 2, and it's a 1 byte value in the heap chunk header, and it's placed right after the previous size. And when a chunk is freed, the heap manager will actually check to see if this cookie is a valid value. And the theory behind it is if you overwrite the cookie, you have to overwrite that cookie to get to the forward link and back link of an item on a free list. So if the cookie's changed, well, then the heap's corrupted, and you can not unlink the chunk. It should, you should see though that it's only 1 byte. So if you have an application that doesn't crash, you can practically brute force the heap cookie because it's only one of 256 values. And we put a little code snippet down at the bottom of the way they check for the heap cookie. It's based on the address of the chunk, and that's the random kind of value for it. We talked about safe unlinking already, but we'll go over it one more time. I just like to think of it as it checks the chunk's forward link's back link and the back link's forward link both point to the same place. If that's true, then check to see if the chunk's back link's forward link points to the chunk being freed. If that's not the case, this item doesn't belong on this linked list, and hence you can say the heap has been corrupted somehow. Process termination, I think we talked a little bit about. This is more of a Vista Server 2008 Windows 7 thing where if the heap actually reports corruption, the application can terminate instead of just continuing its execution flow, such as in XP. Oh, and in 2003, we've came across some corner cases where it will actually raise an exception when the heap's corrupted. So that kind of can mess your exploitation up. If you come into one of those cases.
All right, so is my mic? Okay. Let's talk a little bit about exploitation tactics. First, I'll cover stuff that briefly, where you have the usual problem of not having enough time, but I'll briefly go over the sort of 3 best of breed exploitation tactics that are published already, and we'll build on those with our the rest of our presentation. So the first one, and this one is a mainstay currently of SP3 exploitation, is the look-aside linked list overwrite. So the look-aside front end is there for performance, and it's meant to work in highly concurrent code, so it uses an atomic compare and swap and uses a singly linked list. So basically it can be thread safe because it's obstruction free. So basically, this is good for people trying to exploit things because it's a singly linked list with no security checks. So this ends up being a very useful technique. Basically, what you want to do is overwrite a buffer that is on a look-aside list, and then you can corrupt the forward link pointer.
And we actually use this in our one vulnerability. We use this technique as one of the stages of gaining code execution.
Yeah, and also this is useful for extending limited corruption into a more general form of corruption, because you can use the look-aside list as an intermediate step to extend a 4-byte corruption into an n-byte corruption in an arbitrary address. And we'll kind of show how to do that in the demo. So look-aside lists are important. The other very useful tactic is free list zero attacking. So there was 2 observations that Brett Moore made in his original paper and in his Black Hat presentation. Yeah. The first is that linking doesn't have any security checks. So when a block is placed into the free list, there's nothing it really, well, there's a couple things it can check, but it can't do the same level of robust checking that the unlinking does. And the second thing is that the safe unlinking it calls that function labeled terminate or report heap corruption, but it doesn't actually terminate the process. So it continues execution flow after that if statement. So these are really complicated logically, and we'll kind of go over them a little bit with the heap cache attacks, but basically you want to read Brett's paper.
It took me a few readings of Brett Moore's paper to figure it out, so I don't think we can do anything in 10 minutes here. Read his paper.
But so the third one is bitmap flipping attacks, and this is also covered in Brett's presentation, and it's credited to Nicholas Weissman at Immunity. But the basic idea is that there's the bitmap, which indicates whether a entry or whether a size in a dedicated free list is empty or not. And basically, you can use various tricks to set an entry in the bitmap for a free list. And I think
yeah,
okay.
Here we go. So as John was just previously talking about the bitmap attack, being that the bitmap is actually on the heap base, you can, if you can get it to think a free list is actually populated when it's not, you can write down the base of the heap. And previously we just talked about the commit routine. Overwriting that to function pointer, you get the heap to extend, and you can then work on turning off dep. But yeah, Nicholas Weissman kind of gave this little riddle out on the Daily Dave a couple of years back, and he obviously knew the answer, and everyone else struggled to figure out what he was talking about. But he said, if you could increment an arbitrary address, what address would you choose? And he was trying to lead that you should overwrite the free list and use bitmap, because if you could increment that value, you could potentially get it to think that a dedicated free list was populated when it wasn't. Well, the thing about that is you usually don't get to choose what address, or even know what address you want to increment. We found out that if you can overwrite just the size of a block that's the last chunk on that free list, you can actually get it to update the free list and use bitmap for a size that maybe you can control. And we'll look at some code.
Yeah, Brett, this was Brett's.
Oh, it was?
Yeah.
Okay, I apologize. So I guess we'll go over the code quick. John, do you want to go back and forth, kind of how we practice? So if you look at this code, there's a few things. You see you get an entry. It tries to perform a safe unlinking, and then it tries to check if next equals prev. That is the free list empty? If it is, get the size from the entry that you just found, and then update the bitmap accordingly based off that size.
So there's at least 4 problems in this code.
Yeah.
Okay.
All right, the first problem is it checks to see if next equals prev. That is it empty? Well, if you control a 16-byte overwrite, you can actually make the 2 addresses readable addresses, and then it thinks that free list is empty, whether it is or not. And you can lead that to code execution. The second issue is the size updating. As you see, John will point out that it's directly taken from the entry you found. And we just talked about, if you can overwrite this, well, you control the size. And like I said, if it's the last entry on the free list, you can update the bitmap accordingly. The third thing is they used an XOR to update it instead of just setting it to 1 or 0. And that means you can get it to update arbitrary bits in the free list, when in reality, if it's empty, you should just set it to 0 instead of XORing it, because if it's already empty and you trick it into being empty again, you can get it to turn and think it's actually populated in that sense. And last and finally is it doesn't check the size is less than 80. That means you can actually write past where the free list and use bitmap is on the heap base. And this means you can toggle bits in the big baby Jesus of heap data structures, which is the base of the heap. And from there, we worked on flipping bits to get the commit routine set to something we want, and then you go for the win from there.
Yeah, so basically what you do is you overwrite, if you're overwriting a chunk that's on a dedicated free list, you'd overwrite a large size, and that would end up updating the bitmap for that entry for that size and toggling a bit that happens to correspond to the function pointer. So if you spread the heap, you could pick a nice bit to point the function pointer at a predictable address.
Yep. Okay, this is something that John and I, or at least I claim John and I found almost simultaneously, but now I think he claims he found it 3 months before I did. The look-aside list is actually wrapped in a catch-all exception handler. And I believe the reason they do this is if an allocation fails from the look-aside list, the next step in the process is to look in the free list. So they just assumed catch-all, worst-case scenario, it goes to the free list and uses that. And we thought about this, and we thought of ways that you could, make this to your advantage. Well, if you can overwrite quite a few entries in various look-aside lists, you can try to do some like stack guessing or PEB guessing. And the example I came up with was So there's, randomization of the PEB somewhat. Guess a bunch of PEB locking routine addresses and populate those in subsequent look-aside lists. Then make allocations for those sizes. If the look-aside list fails, you're going to get your memory by the free list. No harm done. You write whatever. Now, if it succeeds, which is it found the PEB locking routine, you get it back, and then you overwrite the locking routine, and it's just like old times where you can get code execution that way.
Okay, so, it's a big slide. So heap cache, we just released a paper on this yesterday, I think, but we'll cover it here. So the heap cache, the free list 0, we know contains it's a doubly linked list, a sorted list of all the free chunks above or equal to 1024 bytes in size.
From smallest to largest.
Yeah. So if there's a lot of these, every time it wants to access the free list 0, it has to iterate through all of them. So what the heap cache is it's a runtime performance enhancement. Basically, it's an index. I have a diagram here. Yeah. So you can see in the diagram we have, this is a free list. It's a very simple free list 0. It's got 3 entries. And here is the heap cache. And you can see that the heap cache, so our entry in the free list 0 is, we have an entry for 91, 211, and 268. Now, the heap cache isn't started when the process starts up. It's added based on runtime heuristics later. So this could exist without the heap cache and there'd be no problem. But later on, if it invokes the heap cache, we see now that we have this index into the array. So bucket 91 points to the entry at 91, 211, 268. So the size of the heap cache, the number of buckets, is calculated based on several different configurable fields in the taken from the PEB and the flags to create, process into heap, create heap, and alloc heap. But basically, in the default setup, in the most common case, it's going to be 896 buckets. So basically, everything between 1K and 8K will be indexed by the heap cache. So let's see. All right, so let's talk about the runtime heuristics. Basically, it only wants to invoke the heap cache if it observes that a program could benefit from the performance improvements. So there's 2 ways it can detect if it should invoke the heap cache. The first is if there's 32 entries in the free list 0. And right here I gave kind of a simple pattern as to how you could create that. This would have to be translated into whatever actions you have in the program you're attacking. And the second heuristic is over the process lifetime have 256 blocks have been decommitted back to the kernel. So the premise of the heap cache attacks is that the primary key for the heap cache is the chunk size. So if we overwrite the chunk size, it's no longer going to be able to look up entries in the heap cache correctly. So we leverage this to basically desynchronize the index from the linked list. And this essentially gives us a stale pointer, which we can extend into other exploitation primitives. So we have pictures. So we'll start with the simplest form of a desynchronization attack. So we're going to show how to exploit a 1-byte overflow of a null into a heap chunk. So there's nothing up our sleeves here. We have a normal free list. Again, I'm using the simplified 3-entry one. And then we have a heap cache that indexes it. So the first thing we'll do is we'll assume that we have a memory corruption vulnerability that lets us hit 1 byte here in this buffer. So we would be writing from a buffer in contiguous memory previously to that buffer, or some other more subtle type of vulnerability that let us directly do this. So we can see the only thing that's changed is we've written a null byte there. So basically, the system is okay. We can see that there is a problem in that the bucket for 211 now points to a heap cache entry of size 200. So what happens when when our program makes an allocation later, and we'll say the allocation is for size 200 to keep it simple. What will happen is the heap manager will go to the heap cache. Will say, okay, I I want to service it with this request. It'll unlink it from the free list correctly because that code's solid. But when it goes to update the heap cache, it'll say, okay, I want to update the heap cache, delete entry for size 200. And then the heap cache code says, well, I don't have an entry for size 200, but I'm not going to worry about it. I'll just return. So that leads to this situation. So now that we've done one allocation since then. So the free list is still valid, and it's fine. You can see it has 2 entries, and nothing's been corrupted, or nothing's going to crash on you out from under you. But when you look at the heap cache, we have this stale pointer there. So in bucket 91 and bucket 268 are fine. They're pointing to the actual valid heap free list 0. But the entry for 211 in the heap cache is now pointing to a buffer that's been handed back to the application. Now, we'll stop here for this attack, and we'll assert that the application writes valid pointers to the first 4 bytes or first 8 bytes, or otherwise doesn't touch them. And what will happen is subsequent allocations for the vulnerable size will all return the same address. So essentially, you can from there you can likely figure out a way to exploit that, because basically any allocation by the application that uses this stale heap cache entry is going to end up returning the same address over and over and over, which is not good.
And you'll be talking about the insertion attack next. And basically, you can think of it, the first time you want to allocate that, you'll write 8 bytes. The next allocation still thinks that the pointer in the heap cache is a free chunk, so the 8 bytes that you just wrote are considered the forward link and the back link. And this is where the insertion attack comes in, and you can use that to your advantage, as we talked about previously.
Yeah, so the insertion attack continues on from where we left off in the last attack, so we'll catch back up. Everything's like it was. We do the 1 byte overflow. So this time we're going to posit that this allocation that follows the 1 byte overflow, that we as an attacker can influence the contents of the first 8 bytes. So imagine like it allocates a buffer to read in a network packet, or to get a segment of an MPEG file, or something like that, pull a chunk out of a RIF file. Or so basically the premise here is that we're going to provide an F link and B link of our own choosing. So this buffer's marked busy, but it's interesting that it will return it back to the application, and it'll also use it as part of a valid entry in the free list. So let's see.
Yeah, right there on the next slide. You want to what you want to do is determine the size, and then get something linked in before the chunk that you just overwrote the forward link and back link. That way, when it tries to adjust the pointers, the malicious backlink that you provided, the address of the chunk you just freed gets written there, and then you can continue on.
Yeah, so right here we show in the 8 bytes that we control, we provide an F link, and this is a placeholder for basically a place that we want to further extend our corruption using the look-aside list technique. But the B link points to back to the base of the heap. And here, when our buffer is linked in before the malicious buffer, what it comes out to is the second look-aside entry ends up pointing into the ends up pointing basically 3 allocations from now of that size. Yeah. Our pointer will return back to the allocation.
Since the backlink is overwritten with the size of the chunk, it goes size of the chunk, its forward link, which points to the forward link of the chunk that we overflowed to give it the malicious backlink. So you use the forward link for a place that you want to overwrite eventually, and the backlink of a way to start the write n bytes process in the look-aside list. And we do that in our demo, and I'll show you that in greater detail.
So we've posited a lot here. So kind of to double back and reduce our preconditions. In the real world, things aren't this pretty. We're not going to be able to predict the sizes. There's going to be multiple threads. It's going to be a lot harder than that. So we've kind of pared it down to the absolute minimum that you need to do this stuff. And one of the techniques we came up with is we can use the heap cache to create defensive sort of barriers to non-determinable or unpredictable behavior in the application. So we called this the shadow free list because it sounds cool. And basically, I can show you, let's see.
Yeah.
So here, look at the heap cache. Here we have entry 92, which using the desynchronization attacks, we have a stale pointer in. What we did was we made a valid entry for 91 and 93, so that 91 and 93 point to the valid free list, but entry 92 points to our malicious free list. The cool thing about this is the application will have to directly try to allocate a block size O by 92 in order to receive our malicious value. So we can kind of narrow down to a specific size what will end up affecting.
And this gave us a lot of problems when working with these vulnerabilities. Is we would override a size, get our stale pointer, but before we could take any farther action, the application was allocating memory so quickly that it just used one of our stale pointers, try to do something, or the block split, you know, and the program would crash. And the shadow free list is a good way to kind of mitigate against that to a certain extent.
Okay, so how are we doing?
37 minutes.
Cool. Okay, so there's one more attack against the heap cache, and that is, we saw that it's an index into the free list. So each index entry can logically refer to multiple chunks. So the thing to note is that if your block isn't on the free list directly, isn't in the heap cache array, but is indirectly referenced because it's the same size as the block that is in it, it's when it removes your block, or when it removes the first block from the heap cache, it's going to use the forward link in the heap cache to find the next block, and it's going to take that value and put it into the heap cache itself. So this is a slightly different variation on the attack. What we're doing here is we're trying to actually get an invalid value in the heap cache. So basically, you can do this for the dedicated heap cache entries or for the catch-all block. And here we show what we do for the dedicated block. And you can see that we overwrite the F-link with an address at the base of the heap, 150.210, which we kind of represent here what that looks like logically. And that works out to be pretty useful because it will eventually end up returning a pointer to the base of the heap.
Big
and we can hit, yes, we can hit O by 57C. And this is just showing it for the non-dedicated free list. Okay.
Strategy, want to go through
Sure.
these? Good.
Okay. So we're talking about a general strategy, and it's useful when you think of the heap to conceptualize it as multidimensional. So to conceptualize it as being in 2 dimensions primarily. The first is obvious, it's the contiguous address space of the blocks in the heap. And the second is sort of its logical position in the free list and heap cache. So it's useful, like when you want to predict or model or control the heap state, it's useful to think about both dimensions. You want to create holes to control it deterministically in contiguous memory, and also you want to use sizes and timing to control logically where it ends up.
That chart makes a lot more sense after you do this for like 4 months straight. So,
but you lose your capacity to speak English.
yeah, there's a lot of sacrifices to be made.
Trade-offs.
Coherent thoughts no longer exist.
You think in heap blocks. So there's kind of a general strategic question when you're attacking heap overflows. And if you've been around for, I don't know, a decade, you've probably flip-flopped on this a few times. But is it better to attack heap metadata or to attack application data? So there's pros and cons to both. The main pro of heap metadata is that you know where it is usually, and it's usually, it's either like the base of the process heap doesn't move much, and if you're overflowing into a chunk header, you pretty much know where it is, because it's going to be the X number of bytes past the end of your buffer. So obviously the downside is that it's been hardened for some reason. So the application data approach, this is what, back in the day, what you'd do for BSD and vulnerabilities where there wasn't inline heap metadata. But basically, and this is where I think things will be going for Vista in 2008. But basically, you're targeting the application data. And the useful thing about this is that the function pointers aren't going to be hardened, that kind of thing. There's usually good stuff to target. It's a rich target environment. The problem is if you're not overriding something in the same block, then you introduce a lot of uncertainty because you need to know what you're overriding, basically. Okay, so as far as strategic approach, or as far as heap modeling and heap prediction, the current sort of best of breed techniques are heap spraying, which everyone's probably familiar with. That's just filling the heap up with predictable values. And heap feng shui was kind of taking a different tactic, and this is in the context of a programmable or programmatic exploit, like in a browser where you have very fine control over allocations. But basically, Alexander Sodorov, he modeled the heap manager internals in order to create a predictable setup with where he was targeting a object pointer overwrite. But he was able to use the lookaside lists to create a data structure in memory that could be mapped to an object pointer for an exploit. So we have kind of a general process that we've been working on as far as how to make progress in a heap exploit. And I'll go through each one. So the first thing you want to do is try to get your bearings, try to figure out what's going on. You probably found the vulnerability, or you may have fuzzed it out, or something just crashed, but you probably have a good idea of how to trigger the vulnerability, but you actually need to understand quite a bit more about the application and its allocation behaviors. So some good questions to ask are, is the heap cache going to be invoked? Can we invoke it? Do we want to invoke it? Is there a lookaside list? Is it using the LFH front end? How populated is it? What did the lookaside list look like? That kind of thing. Basically, you just want to get a feel for the behavior of the application. Then the next step is to isolate actions and correlate actions. I'm using this kind of a general sense, but to correlate, it can change depending on the nature of the software you're attacking, but if correlate an entry, a record in a file, or correlate a network command or a datagram to a certain set of allocation. Immunity Debugger has a nice function, funsniff, which will show you the allocations that result from a single function.
And again, this is one of the problems we had to overcome because when attacking this network application, one of our requests would generate 30 allocations. And when overwriting things, this turned out to be a huge disaster because it ended up being, originally when we started doing it, it was timing. Timing would determine whether it worked, and luckily we spent a few hard years, hours. It's all relative now. We spent a lot of time on it.
So for timing, what you want to look at is allocation life cycles. So you want to find something where you can have some control over when it's allocated and when it's freed. And in general, for another useful idiom to try to isolate is a memory leak, a long-living memory leak, like something that exists the entirety of a connection and the connection has a long timeout or something like that. Or just a memory leak in the classic sense of being a permanent memory leak, like it allocates something and never frees it. Because you can use these to normalize the heap and to basically get rid of things out of the free list and heap cache that are bothering you. So the next thing to do is you want to take the system from an indeterminate state into a predictable state. So there's a number of patterns we lay out in the paper for actual, when you get down to the detailed allocations. But basically what you want to do is you want to say, okay, I want to wipe out the heap cache, I want to wipe out free list, basically by doing a bunch of long lifecycle allocations. So once you get the state into a predictable baseline, which can be easier said than done, from there you want to proceed to attack contiguous memory. And the usual pattern used there is 3 buffers the same size where you free the middle one. And then After that, you want to fix the buffer in logical memory with the sizes. So, okay, I thought this was funny.
Yeah.
So as far as tools and you're going to want to eventually start. The first thing you really have to do is you're going to need to reverse the heap manager, more or less.
Spend weeks in NTDLL is basically what you have to do to get a start, I believe.
Yeah, so that's kind of because you're going to end up hitting corner cases that you're going to want to know what's going on, and eventually you're going to end up breaking down and reversing it. So might as well do that
sooner than later.
But there are several tools, and we've used a fair bit of them. Ultimately, we settled on Immunity Debugger. And we kind of highlight here some of the functions that we found useful, and we have made some modifications that we'll be taking back.
Yeah.
Okay.
All right. So now we're going to do a demo, actually a video of a demo of a vulnerability we found, and I'll kind of explain briefly what's going on as we go through this. This is to prove we're not lying, also, which it really doesn't prove because it's a video, but whatever.
Yeah. The problem is not that it doesn't work, it's that the bug hasn't been disclosed yet.
Yeah, exactly. We got to be.
So if you really, really pay attention, you could probably figure out what it's in, but if you do that, you're a jerk.
Yeah, don't do that, please. The first thing to show, this is 2003. Dep's turned on for all processes by default. That's an opt-out architecture, I believe. The first thing we're going to do is look at the heap cache. And the heap cache at this point contains a lot of entries. This was a huge problem for us because every time you restarted this program and let it run, the heap cache wasn't consistent. We never knew of a size that we could allocate, where the next chunk would be in contiguous memory. So the first thing we were going to do is, after flailing around for a month and a half, we decided to actually make a plan on what to do. So we decided to send these hard memory leaks. We found a hard memory leak. That is a memory leak that a buffer was allocated and never freed for the lifetime of the process. And this is the first step we took. Clear out the heap cache, normalize our data, get a nice baseline of everything. And you can see we're printing out the heap cache. These are representative of literally hundreds of requests. And finally, after sending all those hundreds of requests, we have one entry left on the heap cache. And this is exactly what we wanted. We needed one entry or no entries, and the size needed to be less than 200 blocks, which is 200 hex times 8. And we've consistently got this to work in this state.
Yeah, the point of that step is that to go from any possible state of the system to a predictable one.
Exactly. And after this, what we wanted to do is free a buffer of a size that we knew. And the way we did this is, Nico Weissman talks about this in his paper of soft and hard memory leaks. A soft memory leak is kind of a timing mechanism. You can control when it's allocated, and you can control when it's freed. So what we did is we said we needed a size of approximately 200, give or take a few bytes. So we surrounded, when we made the allocation, we would do an allocation via the hard memory leak, an allocation for soft memory leak, and a hard leak. That way, there was no chance of this block being coalesced because it would be between two busy chunks and gave us a predictable size. Once we had a predictable size, we could split it in half, and we knew what would be returned to us, and we also knew the size of the next heap chunk in memory because it's been split, which we talked about in knowing the size. That was one of our preconditions. We needed to know the size. So instead of just guessing, we figured out a way to do it, and by we, I mean John. All right, and after that, you can see the block is split in two chunks. As I talked about before, we have a size of E7 and a size of 120. And when I say these sizes, we're going to talk in block sizes. That's the size multiplied by 8 in bytes. And you can also already see the size that Immunity Debugger reports isn't actually the size of E7. It's 03F1. And I put a little diagram in there to show that. You can see right here, it's 3F1. This was a size that we could overwrite it with. this overflow wasn't your typical overflow where you control the data. We only can semi-control a number, a D word, that would get overwritten.
Yeah, between 0 and 3 at that.
Yeah.
Roughly, but it was
roughly.
very.
Yeah, and there was gaps in between. So it wasn't like we could just control whatever size we write and write bytes. This probably took the longest part of this exploit. I think when I wrote the exploit, I did the look-aside list technique and anti-dep in like 3 hours. This was like 2 months of work to get this to work. I just wanted to explain that because this video doesn't really show how much work we put into getting the heap normalized and overwriting with a size that could be useful to us. Also with 3F1 as the size, we needed it to work out so the flags were also busy. That way the block wouldn't be coalesced and wouldn't be marked as free because it was already in a free list or allocated. And that was another precondition. The preconditions for this exploit are literally a page long, so it was quite a bunch of work.
Well, they're not. Yeah, I mean, it works.
Yeah, right. Listen, work is a relative term. Okay, so now I'm going to show you that's the address of look-aside list 38. It's empty right now. We're going to use that as our stepping point. The reason I chose that is because look-aside list 38, when profiling this program, was hardly ever used. And I wanted to pick a look-aside list that wasn't ever used by the application, so when we wrote data there, I know it would be our data, and nothing would request it, and it wouldn't get mucked up. Next, we're going to look at another address. This is a function pointer I found, and actually a table of function pointers. We're going to overwrite this, and that can start our anti-dep process. And we can thank Skate for that because he put out an awesome paper, and that's what I followed to turn off dep. Okay, we're going to go back to our logs now, and the logging window that is, and we just performed 2 operations here. Even though it happened pretty quickly and you can't really see it, we requested a size that would be fulfilled by E7. We requested E0 and overwrote, like we talked about, the forward link and the back link. We overwrote the forward link with the address of that function pointer. We overwrote the back link with the address of look-aside list 38. Then we had to pick a size that we knew was smaller than E7 or E0 in this case, and get it linked in before that entry. So another precondition of this was we had to make sure not only was E7 and 120 there, but there could be no addresses less than E7. That way we can do the insert attack. The backlink's address gets written with the chunk we just freed, and we're going to go to the debugging window again, and I'll show you that the previously unpopulated look-aside now actually has a value. And this is just like the diagram we've shown before. There's the address of the chunk we just freed, its forward link, and our function pointer, our bogus forward link that we just put in there. Basically from this, 3 allocations away from overwriting the function pointer. And I misclicked there, going around. And we'll also show, again, the function pointer is not overwritten at this point. We're going to go back to our logging window, and now we'll do 3 subsequent allocations for E0. That is, the stale pointer never gets updated, right? So you can keep requesting to get the same chunk of memory every time. And we would just overwrite it then with data that we want to use, that is. And now you can see that function pointer is overwritten with an address, and that address is push EBP, because I know in another subsequent request that EBP holds our payload from that network request, and then a pop ESP. We can credit this to Brett Moore, right, for heap to stack flipping. Basically, at this point, you turn the heap data, and since it pops into ESP, it's then running from the stack. So you can then prime the stack for turning off dep, per se, and that's what we did in this case. Now we make the call, and you see we hit our int 3s. Dep should have prevented this, but we'll go look at the process window, and you can kind of see on the right a little bit how we primed the stack. You'll see a bunch of no ops and a bunch of int 3s and some addresses. all the processes have depth, still turned on, except for the one we just turned off. Turning it off let us execute code from the heap and mark the memory page as read, write, and execute, I believe. That's about it. I know. I probably want to explain too that this was a lot of work, and it's hard to push it into an hour. We have a 84-page white paper on all this stuff. If you are really interested, you can probably go read that. And John just posted a blog yesterday on his heap cache paper that goes over all the heap cache stuff in very high detail. So if you want to learn more about that and kind of using these methods to exploit vulnerabilities that are seemingly bleak. Also, there's been vulnerabilities like this. I've seen advisories where they basically said this is unexploitable. It could be only exploitable in the browser, and we just took that as a note to spend months of time proving that it wasn't.
So I think that's it.
That's it.